let's go over one of the proofs in the sample exam. Now remember, in this proof we had a pseudo-random function family f, and using that we constructed a pseudo-random function family z. Z k of x was computed as follows, just to remind you. If x is equal to the key k, then it returned 0. Otherwise, it returned whatever fk would have returned. So it returned fk of x. So this is how we define z. And the theorem we are trying to prove is that if f is a secure pseudo-random function family, then z, defined as follows, will be a secure pseudo-random function family. Let's remember our proof strategy. So whenever we are trying to prove something, first start by writing down the theorem. This is step number 1. Number 2 is writing down the proof methodology strategy. Essentially, this is writing down the contrapositive. So if there exists a probabilistic polynomial time adversary A who has non-negligible advantage in distinguishing zk from a random function. So essentially, A is breaking z. Okay. Then we construct another probabilistic polynomial time adversary B who has non-negligible advantage in distinguishing fk from a random function. So essentially what we are saying is, if there exists a PPT A that breaks the security of Z, then we are going to construct a PPT B that breaks the security of F. So eventually, remember, this would mean if F is secure, then Z must be secure. Let's do this proof. Now, the third thing we should do is to define these interfaces. So here is A. What's the game A is playing? Remember, A is trying to break Z. So this game should be the game for Z. When you think about it, the game for Z is a PRF game, so A is given the security parameter. A can ask polynomially many, polynomially many queries. So it will give us some x, we need to give y, which is zk of. So y needs to be something of the form zk of x. This is what it expects. And eventually it will tell us, okay, are we giving him random or pseudo-random? So y needs to be either zk of x, or it needs to be some, let's say, z prime of x for a random function z. That's what A is expecting. Now, what's the game B is playing here? B is trying to break F. So this is the game for F. For F, again, this is a PRF distinguishing game. B is given a security parameter. B can ask, again, polynomially many queries to its challenger. It will give x prime, and it will get y prime such that y prime is either fk of x prime for a randomly generated key k, or from the same domain and f, the domain and range, a function f prime will be randomly picked out of all possible such functions with the same domain and range as fk, and y prime will be computed as f prime of this x prime. So either one of these will happen, and y prime will be given to B, and B needs to guess, was this function used for computing y prime a random function or a pseudo-random function? That's what is going to happen. So this is the third thing. The fourth item is filling in the code for B. In this proof, it turns out to be extremely simple. B just passes this security parameter to A. Whatever query A makes as X, B will set X prime the same as X, and then query its own challenger. Remember, for this challenger, we know exactly how it will behave. It is here. We know it will behave either the blue way or the green way, and it will return Y prime. B will set this Y the same as Y prime, and then give back to the adversary. So for every query of the adversary, B will do this. And then at the end, its job is again simple. If the adversary says random, B will say random. If the adversary says pseudorandom, B will say pseudorandom. This is the code for B. Now we switch to the fifth item, showing that B is PPT. Let's say A makes Pn queries to B for some polynomial function P. Okay. Then indeed, B also makes Pn queries to its own challenger. So for every query that A makes to B, B also makes one query to its own challenger. Remember, B's running time is the sum of these. So the time for Pn oracle queries plus A's running time plus the red parts that make up B's code. Now each oracle query takes O1 time. That's the assumption. So this is Pn times O1. This is some polynomial. A's running time is some Qn, which we know is also polynomial. Remember, A is a PPT algorithm. And the red code here, it is just some equalities. So for every query that A makes, we do X prime is equal to X and Y is equal to Y prime. So actually 2 times Pn, let's say, plus 2, one for passing the security parameter, the other for passing the output. So since adversary makes polynomial many queries, this whole thing is also another polynomial, which means the whole sum here, the B's running time, is a polynomial of the security parameter n. Now we are done. We showed that B's running time is PPT. The sixth thing we need to do is to show that B is indistinguishable from a real challenger. So A's interaction with B should be similar to A's interaction with a real challenger. Now realize the following. For all queries A makes for all x's that are not equal to the key, B indeed computes zk of x exactly as a real challenger would have computed. The only difference between B and the real challenger is if the adversary query is x. If the adversary query is x, remember, a real challenger would have returned 0 as output, whereas B returns fk of x, fk of k actually, as its output. So here, the adversary may distinguish. But remember, this difference only happens if the adversary manages to send a query x that is equal to the key k. Now remember, this key k is a randomly picked value. So the probability that A, without knowing this key k, queries for some x that is the same as this k is indeed the number of queries A makes over the key space. The key space, let's say if the keys are n bits, the key space would be 2 to the n. This is some polynomial. Polynomial over exponential, we know, is negligible. So except with negligible probability, A cannot distinguish B from a real challenger. So sixth part is also done. Now, seventh part, success probability, remember. Realize that the probability B distinguishes f of k from some random f prime is indeed the same as the probability that A distinguishes zk from some random z prime. So, probability that B distinguishes fk from f prime is indeed here the same as the probability that A distinguishes zk from some random z prime. Remember, by definition, this is some non-negligible epsilon. This is the assumption that such an A exists that breaks z. Breaking z means distinguishing these with some non-negligible advantage. Now that we showed that B distinguishes with non-negligible advantage if A does so, we are done. So as the eighth item, we can conclude our theorem. Remember, if F is a secure PRF family, then this epsilon, B's distinguishing advantage, must be some negligible function. Remember, epsilon is also A's distinguishing advantage, so A's distinguishing advantage must also be negligible. Overall, we can conclude our proof by saying that this means Z must also be a secure PRF family. So if F is a secure PRF family, Z must also be a secure PRF family.